Hello everyone. So in the last video, we talked about the basics of simple and multiple linear regression. That's the linear model that serves the foundations of machine learning. But there's an even more profound concept, and it's called the OLS solution, or ordinary least squares for short. Okay, so remember how in linear regression, we want our predictions from this linear model to be as accurate as possible. So we want to somehow adjust the slope and adjust this intercept or the weights and the biases, adjust these such that our predictions are as accurate as possible. So we want to optimize our parameters to make the overall prediction accurate. So formally, we want to minimize some loss function or a measure of how wrong we are. The smaller, the better. And one of the common choices we discussed was mean squared error, which is done by taking all the differences between each predicted and true value, or it's also called the residual. So if you predict 5 and the answer is 2, the difference would be -3. If we square that, that becomes -3 squared, which is 9. And finally, we take the mean for all data points in our data set. So let's see the objective. What I just described was the intuition of MSE. But mathematically, you can see it's saying the same thing. It's the difference between y, the value of y, and y hat, in which y hat is our prediction, square that, and then take the mean. As you can see, we've summed it using that sigma symbol over there, and then divided it by the number of um, data points in the data set. That's equivalent to saying the second one, which basically substitutes our prediction for the linear model over there. So that's just our definition. And then we have, if we write that in a simplified or equivalent form, we get the norm form, and then compiling everything else into a matrix, X, then we can write it even simpler like that. But there's also something called the sum of squares errors, or SSE for short. And basically, instead of taking the mean, we just sum it. We don't even divide by the number of samples, so we keep it at that. But turns out minimizing MSE is the same as minimizing SSE. If you've noticed, MSE is just sum of squared errors scaled by n. So it's just that sum divided by the number of data points n. And this time n is fixed, it's static. It could be 500, 5,000. It all comes down to the actual size of the data set, and that can't be changed. That's not learnable in training. Thus, since it's just scaled by this constant factor n, it yields the same minima. Minimizing MSE is just minimizing SSE, just scaled down differently. So now that we've got our other objective that's basically the same, we've got the minimization of the sum of squared errors over there. Okay, how do we expand this? As you can see, this is like a quadratic form, right? So we can equivalently write it as in the dot product form of y minus xw dot product with itself. And expanding that even more using basic algebra, we get the dot product of y, or basically just the squared magnitude, minus the cross term, and then add it again. How do we find the global minimum then? We can use the derivative trick in calculus. By evaluating the derivative of this function and setting it to 0, it provides us with the global minimum. If we differentiate this, we can get -2 x transpose y. That comes down to the middle term. So that first term, the squared magnitude of y, why does that disappear? Because it's not dependent on, w is not dependent on that term. So it's because it's not dependent, you can just ignore that because it basically also scales it by a constant factor and doesn't influence the final thing. So we want to focus on all the ones that actually have w in their term, i.e. all the ones that actually contribute to the final thing. In this case, we have in the middle one negative 2 x transpose y because the rule of calculus, and then plus 2 x transpose xw. That's because, as you can see, we have w transpose, and we also have it again at the end, and thus by the vector matrix calculus and all that, we can see that we just drop that power to 2. Now that we have this, if we just move the negative to the first term to the other side, it just becomes that equation, which then, if we divide everything by 2 again, it simplifies to what we call the normal equations. Now we've got it to a very, very clean form. But how does this help us in finding the global solution? After all, our whole goal behind this is to find the best possible solution, or the one that minimizes the loss the most. Well, we can use the inverse matrix here, the inverse matrix trick. So just to recap, the inverse matrix is a matrix such that when it's multiplied by the original one, it yields the identity matrix, or the one where the diagonal terms are all 1. This is basically like an undo button of the original one. It undoes it, just like inverse functions in high school. So if we see that term over here, x transpose x, that's the term we want to get rid of, right? Because in order to isolate w, that is, if we isolate that, we can find the minimizer, the closed form solution. We have to get rid of the x transpose x, and to get rid of that, we have to take its inverse. So we take its inverse and multiply it by that. And in doing that, we have to do that to the other side too. So we multiply the right-hand side by x transpose x inverse. And thus the left-hand side becomes IW, because remember, the inverse multiplied by the original is always the identity matrix. And because the identity matrix does nothing to the original thing, that's just W. So we've essentially gotten rid of that term. Thus, W equals x transpose x inverse multiplied by x transpose y. That's our closed form solution. And if we have our data and our outputs, so if we have our features and our labels, we can, for any linear regression problem with sum of squared or anything, basically, we can find out the optimal solution just by using this formula. So we don't even need to train it or anything. We just have to slot the values into this formula, and we automatically get the best values for this. We've automatically found the optimal values. So this is very significant because instead of having to go along and use what we call gradient descent and other mechanisms to sort of optimize this, all we have to do is just put this into this formula, and we get a closed form solution. So we already get the best possible solution. The problem with this is inverting this matrix is quite computationally heavy when it comes to very, very, very large data sets. So imagine this matrix X, which is our data matrix basically, is very, very, very big, very, very large. Inverting this would be also very, very heavy, which is why often we only use the ordinary least squares closed form solution for small data sets. For large data sets, we will use something called gradient descent, which I'll discuss later. But first, let's think about why this worked. Well, MSE and sum of squared errors, which is our loss function, is fundamentally quadratic, right? As you can see, going back here, we get the square. Because it's like a square and it's quadratic, it's bowl-shaped. And being bowl-shaped, there's one minimum. So the minimum is that bottom of the bowl, the valley. So it's one global minimum. When we say it's bowl-shaped, there's one global minimum, it's convex. Thus, setting the derivative to 0 gives us the global minimum, so it guarantees us the optimal solution. However, modern neural networks, especially the ones powering ChatGPT and Gemini and all that, they don't use mean squared error. They use some other complex loss functions, sometimes cross entropy loss or other. And because of this, and the billions of parameters, this composition, the complexity of the neural networks, that the optimization landscape becomes very, very non-convex, meaning there's a lot of local minima, there's a lot of bumps and edges. It's not perfectly smooth, unlike our bowl-shaped solution here, in the sense that most of the time when we optimize neural networks like that, we don't often achieve the global minimum, and rather converge at a local minimum. Okay, that sums up the video.